This video covers the details about linear regression, geometric intuition, and mathematical formulation for it. So consider we have two features, um, like uh, say if let's consider we have two features. Let it be uh, weight and height of a person. So if we know weight of a person, then we have to predict height of a person. And imagine the distribution of points is like this. And so what linear regression states is we have to find a plane or a line which is as close as to the data points. And this line or plane is called as best fit. Why it is called as best fit is like we can have so many lines which can be drawn, like it can be like this, like in so many directions, but the best fit line is something which is close to the uh, data points as much as possible. So, and one of the main objective of linear regression is after finding the line of after finding the best fit line, the errors are very minimal. Errors are minimal. What this means is, say, as you can see, there are only few data points or some data points which are present on this line, and some are like a bit away from this line. So the distance from the data point to the line is called is the error. And let's say if uh, oh yeah, let's say if my predict instead of going to the predictor value, the equation of line or the plane is given by y hat equals to w transpose xi plus w0, where w with uh, the W0 and the W1. I'll remove W transpose, or we can have it if it's a plane. Yeah, this is the slope and this is the intercept. Slope and this is intercept. It is similar to our equation of line, right? Y equals to mx plus c. This is for two-dimensional and this is for higher dimensions, multi-dimensional. Now, uh, what it tries to do is linear regression. It has to minimize the errors. That is, yi minus yi hat should be minimal. So yi hat will be on the line, and the yi's are the data points. So the distance between the data point to the line is yi minus yi hat, and here yi hat is called as the predicted value. Okay. Uh, However, if and however, like here, the points above the line, the distances from the points to the line, which are above on the left side, are positive. And here, if I take the if I take the distance from the line to the point below, the distance will be negative because or else this will be positive and this will be negative. Sorry, this distance will be negative because this is yi minus y hat. Oh, sorry. My mistake. This distance will be positive and this will be negative. Yeah. Yeah. So as I said, it has to minimize the number of errors. However, there could be some instances um where like this like positive errors might cancel out the negative errors. Why it happens is, as I said, uh, errors should be minimal. That is nothing but summation of yi minus yi hat should be minimum. That is the best fit line. That's what it tries to do. I also said the positive errors might cancel out negative errors. So what we have to do is we have to square each of the errors for I equals to 1 to n. So this error is called as sum of squared errors. So essentially, to summarize, what linear regression tries to do is it tries to minimize sum of squared errors. And uh, so if I write the mathematical formula for this as similar to a logistic regression, it's nothing but I have to minimize argmin of w comma w naught. I have to find the values of w and w naught for which I can minimize my sum of squared errors yi minus yi hat whole square. And here where y hat is nothing but w transpose xi plus w0. This is the main objective of linear regression. Find the w and w0. That's nothing but optimal values of the weights and the intercept, which can minimize the sum of squared errors. So